All right, everyone, good morning. It's 11 o'clock on the hour, and I'd like to welcome everyone into LPKF Studios right outside of Portland, Oregon. We're going to be here for the next hour or so. We're going to have a half-hour presentation, and we're going to follow this up by Q&A, and we'll be here till noon as long as you guys have questions. So today we're presenting our newest webinar, 3D Circuitry on Thermoplastics. And what are we going to be talking about with that? We're going to be talking about molded interconnect devices and specifically creating MIDs with laser direct structuring. A little bit about people presenting today. My name is Shane. I'm in the marketing department here in Portland, and I'm joined today by Stefan Schmidt, president of LPKF. Thanks for joining us today, Stefan.
Hi, thanks for having me.
And then I'm also with Don Porter, global account manager. Don, thank you also for stopping in.
Thanks, Shane.
All right. So if you have any questions throughout today's webinar, feel free to submit them via your GoToWebinar questions panel. You can see on the right hand of your screen, there should be a little questions tab. And, or you can submit them via Twitter. You can do this by tweeting your question to our Twitter account at LPKF_USA. 1,000 bonus points to anyone who submits your question via Twitter. We're going to go ahead and answer questions at the end of today's presentation. So that way we can keep the presentation as succinct and just moving as quick as possible. So our webinar is entitled 3D Circuitry on Thermoplastics. And we're obviously, as I mentioned, we're talking about creating molded interconnect devices with laser direct structuring. So what's on slate for today? We're going to talk a little bit about the rise, fall, and rise of MIDs. We're going to talk about some manufacturing methods for created molded interconnect devices. And then we're really going to break down the laser direct structuring process, what it is, how it works. And then we have a really cool application section where we're going to break down several MID applications that were created with laser direct structuring. And then we're also going to have next steps at the end. So what if you're really interested in laser direct structuring and maybe you want to check it out? But let's start at the beginning because it's always a very good place to start. So let's talk about molded interconnect devices. Now these are really cool parts. Now basically, if you took a circuit board, and you took the housing for the circuit board, all the associated connectors, and then all the cables involved, and you put them all into one part, you have a molded interconnect device. Now what's cool about a molded interconnect device is that it combines basically all mechanical and electrical functions into one single tidy part. And that's really cool because basically what you're doing with an MID is you're reducing the number of components and you're reducing the number of parts associated with your electronic device. And this has many benefits. Now the biggest ones, it saves a lot of space, it reduces the weight of the part, and it lowers your cost. So, and the other big thing about MIDs is this 3D workspace. As you can see with the MID we have up on the screen, you know, you are limited, you're breaking free from the square circuit board, and you're really able to open up your designs to be ergonomic and really fit your device. It's really cool. A little bit about the history of MIDs. MIDs broke onto the scene like Magic Johnson, cassette tapes, and yes, in the 1980s. Also the decade I was born in. Now, despite early fanfare about the buzz of MIDs, because of all the benefits we just talked about, they didn't really catch on at first. Now, why was this? Well, the main reason was that the threshold for entry into the world of MIDs was really high. Now this was due to the high cost for tooling to create your parts for MIDs, and there's really no flexibility for mixed manufacturing environments or for prototyping. So basically you had high cost for tooling and a situation where only very large quantities could be manufactured. Now in recent years, the last decade or so, demand for MIDs has really skyrocketed. And why is this? Well, today's world, it's all about miniaturization and increased functionality. So, as we mentioned, MIDs save space and they lower part weight by reducing components and bringing what would normally be a mess of wiring all into one single part. And that's a very appealing factor for those trends of miniaturization and increased functionality. In addition, there are now certain manufacturing methods which have been able to bring down costs and allow for smaller volume production to get started. And that really lowered the threshold for entry into the world of MIDs. So because of all these benefits that I just mentioned, MIDs are really found in all industries, from automotive to telecommunications to medical. Now, I wanted to bring our panel for the first time today. Steph and Don, what do you guys think is the most impressive or important thing about MIDs? Stefan, let's start with you.
Yeah, thanks, Shane. I think the most important factor on an MID is really that we really get out of this two-dimensional world that we're all used to, in terms of regular circuit boards, or flex circuits, even those start their life as a two-dimensional item, and really start to think three-dimensional. And that really allows for much higher integration of functionality. And if you think of items that are constrained in space, or where we want a human-machine interface that is necessarily not always two-dimensional, the MIDs can be very beneficial there. The other function really is that we add functionality to already existing parts. Most items today have a housing or something like this, which is basically just a housing. So making this housing or this structural part a smart part and carrying some more functions like a connectivity or wiring function could be a huge benefit of making the part much more effective than just being a structural part.
Gotcha. And then Don, what do you think is an impressive thing about MIDs?
Well, following up on what Stefan was saying, you're combining a lot of functions into one part. So a single part can be a housing, it can be a package, it can be an electrical interconnect within the same part. And so you reduce your part count, you reduce your weight, you cease having a flex circuit and a structural part and a PC board all together, and you start taking these things down and putting them all together in one part.
Gotcha. And you really mentioned reducing weight there, and I remember you were talking to me, Don, and that's a big deal with, no matter what industry you're in, whether you're working in automotive or you're working in medical, getting the weight of these parts down is a really big thing. So how do you create molded interconnect devices? Well, there's several methods, and there's a couple that I don't have up on the screen. There's insert molding, and there's also hot stamping. But I kind of wanted to focus on the two methods you see on the screen, because these are sort of the main two methods and really common methods for manufacturing MIDs. So you'll see I have two-shot molding and laser direct structuring. And despite the fact that there's only two methods on here, I want to say I'm not trying to make it out to be a one versus the other sort of thing. It's just these are the more common methods. So while you look over the table on the screen, Stefan, I wanted to ask you to kind of break down the differences between two-shot molding for MIDs and laser direct structuring for MIDs.
Yeah, the general difference here is a two-shot molding. For those of you who are not familiar with this, basically works with a molding tool that uses two completely separate plastic materials. One of them being a standard plastic, and the other one being a plateable plastic material, basically a plastic that is doped with a catalyst to be plated. Now you can imagine this is fairly complicated to do, and most of you guys probably you think of your toothbrushes that you have at home or something. You see there's two different types of plastics on there, and those are fairly coarse structures. So if you want a very fine small structure, this is going to be very difficult to do. And of course, if your circuitry is being part of this mold, it really can't be changed later on in the process. Now the laser direct structuring is an alternative technology to this, and it really the interesting part is it only requires a single shot injection molding process, and then the circuitry will be added to the part later on with the laser process, and then followed on with the selective metallization. So here with the second technology, with the laser direct structuring, we actually separate the creation of the circuitry from the creation of the mechanical part, the injection molding, and keep both parts much less complex there.
Yeah, being able to keep those two separate functions separate, I know, is a big thing for me, and allows you to make more changes later on in the process, which is someone who's a creative individual myself, like a lot of our designers out there, that's a big thing. Stefan, I wanted to ask you about the differences between manufacturing volume and production quantity, comparing two-shot molding versus laser direct structuring.
Yeah, the two-shot molding is an interesting technology, especially when it comes to very large volumes, and when it comes to parts that either the parts are structurally very large, or they have very large areas that need to be plated, and they're not necessarily too complex. So in that area, it can be interesting because you can basically injection mold those parts and then continue to produce them. However, again, the threshold to produce this is fairly difficult because, again, your circuit structure is part of the mold, and that's a very complicated, time-intensive and expensive process to do. So separating those two items can be very helpful. Now, so in the past, we have seen two-shot molding for MIDs really only for high-volume parts, and the laser direct structuring over the course of the last 5-6 years, we really have seen a big change in that that MIDs now become more popular for smaller volume, but as well as for large volume productions, because now things can be done a much quicker turnaround there.
Exactly. Now, obviously, we're going to be talking about laser direct structuring, so I wanted to bring that up here. And we're going to break down laser direct structuring. Now, what's cool is it's a really simple 3-step process. It's a physiochemical process for creating 3D circuitry on MIDs. Now, laser directed structuring, you're going to hear us refer to LDS a lot. We're not talking about Latter-day Saints. We're going to be talking about laser direct structuring. So if you hear LDS, you'll know that's what we're talking about. Now, the 3 steps are pretty basic. First, you have injection molding. Then you have laser activation. And finally, you have metallization. So the first step, as I just mentioned, is injection molding. And the big deal with laser direct structuring is that it's one-shot injection molding of doped thermoplastics. Don, I wanted to bring you in right here. Why don't you talk a little bit about one-shot molding and how it's different than two-shot molding?
Well, Stefan pointed out that the two-shot molding process can be a fairly complex tool. The mold itself has to have cavities for both types of plastic in it. And in this case, when we talk about a plateable plastic, you're talking about plateable plastic and then a non-conductive plastic. Laser direct structuring allows you to use a single type of plastic, and that's in a single shot mold. So one mold, basically the shape of the part. The plastic is doped, but in its raw form is non-conductive. It's only conductive when you apply the laser power to it and define the pattern that you want to plate. The plastic itself is available from all major suppliers. So the people you're buying your plastic from now all carry an LDS grade of plastic, and in basically all the formulations, various formulations of plastic that are available.
And Don, I know Stefan was comparing two-shot molding to kind of like a common example would be the toothbrushes, and I remember you kind of had the perfect example for one-shot molding, and what was that?
Well, I was bringing up the little green army man of our youth. Shane probably doesn't remember this, being born in the 80s, as he pointed out, and being such a young pup, but we played with little green army men when we were kids, and I guess Toy Story brought those back, but it always reminds me of that, a very simple casting, very straightforward molding process.
Gotcha. Yeah, I am pretty young, but I do remember playing with little green army men. And then, Stefan, I actually want to ask you a little bit more about what are some of the types of plastics that are available in LDS grade?
Yeah, so in LDS grade, there's a lot of materials available right now, and it stretches the entire bandwidth right now. Anything from very commonly used PCABS materials for many consumer devices over to nylon grades that are often used in automotive type applications, and then we see a lot of LCP or liquid crystal polymer type grades in micropackaging and medical applications. So again, pretty much the whole spectrum's out there. And again, it's reputable, plastic resin manufacturers that create their particular materials in an LDS grade.
Gotcha. Now, as we go through the 3 steps, I kind of wanted to, in a way, create a part. And so once we have done our one-shot molding of our part, you'll get something like you see here. And we'll add each layers of LDS to this as we go on. But here you can see a very simple one-piece part. Now, the second step of laser direct structuring, or LDS, is laser activation, and this is really cool. Basically, it's a physiochemical reaction that etches the wiring pattern for the part onto the plastic, and it prepares the material for our third step, which is selective metallization. I wanted to bring back in Stefan to explain how the laser activation works, because it's really cool.
Yeah, so here on the screen you see basically the matrix of the plastic material, or a representation of the matrix. The dark spots there is basically the plastic material. Like I said, it can be anything from a PCABS to an LCP and anything in between. And then the material has a catalyst compounded into it, and the catalyst has a couple of interesting features. It's based on a metal, so it's a part that would attract the plating. But this metal is packaged in an organic packaging, so it's non-active in its native form as it's compounded into the plastic material. And on the upper right side of the screen, you see these black dots in this big yellow area, which basically the black dots are representing the catalyst being compounded uniformly throughout the plastic material in its native form after injection molding. So that's what the part looks like after molding. So it's ready to be activated, but it's non-active in its current form. Now, when we hit it with the laser right now, then there's a couple of things that happen right now. And the most important part is that we actually crack open the packaging of the metal in the catalyst, and basically let the metal be active, but only in those areas where we hit it with the laser. So again, if you look again on the upper right side of the screen, you see that plastic material with the catalyst throughout the material, and then you see these green dots on the surface, which represent now our activated areas. Now those are the areas where we basically cracked open the packaging of the catalyst, and that's where we plate in no other area, which makes it pretty attractive. We can plate in only certain areas, and it's not a function of the molding at all anymore.
Gotcha. Beautifully put. And so here what you'll see on the screen now is basically this is what you'll see above the molecular level of this is what your plastic will look like. On the left you have your laser activated surface, and the right you have your unactivated surface. Don, talk a little bit about what we're looking at and the importance of that left side of what we're seeing.
Well, you see the smooth unactivated surface on one side, and that's basically your mold skin coming out of the mold, and it's not very platable as far as peel strength. It's a very smooth surface. In two-shot molding, a lot of times you have to add a chem etch step to get some roughness, so that your plating will actually hold to that surface. You get rid of the smooth mold skin. The nice thing about laser direct structuring is that within the activation procedure process, in a single step, you actually roughen up the surface also. So you get a very strong adhesion to the plating and a very, very high peel strength.
Gotcha. Getting that peel strength is really important. We're going to go ahead and actually look at a little animation here of what the laser activation step of laser direct structuring looks like. Stefan, why don't you explain to everyone what we're about to see before I play the clip?
Yeah, so you see on the screen here basically what one of those laser machines would look like on the inside that does the laser activation. So here we're representing multiple laser sources through those different colors. We have a blue, a red, the green, and a yellow laser. Of course, in real life they're not these type of colors, but we use the colors to just basically to show that we use different lasers simultaneously. And that's really a representation of how we would use the system in a high volume mass production environment for consumer electronics devices, for example. So you can see it's not only limited to prototyping or small quantities, it's really full volume. So if we roll the tape right now, we will see how those lasers will work all simultaneously and activate the area in all different spots right now. So we have lasers hitting it on the side, on the top, from the back side as well. We have lasers working on one end of the part, on one side of the part, while another part is being loaded and unloaded. And as soon as the structuring is done, it switches over to the next side and structures the part again. And again, the loading and unloading can be done at the same time. So again, very efficient process for very high volume manufacturing there.
Gotcha. And then if we were to take the animation away and then see what would a real part like this, so we'll take our part that we molded with the one-shot molding in the first step, we'll laser activate it, and this is what you'd see. You see you'll basically have the outline for your wiring right on that part, which brings us right into step 3, which is metallization. So now that we've laser activated it and we've roughened up that surface, we're going to do an electroless copper plating. And once you've put it in the solution and you've let it do its thing, you get your metallization on the surface. And right here on this slide, you can see what the layers of metallization look like. Stefan, talk about the different layers and the way they attach.
Yeah, so here we see a cross-section of a plastic material and the plating on it. So on the left side of the picture, you can see the dark area on the bottom, which is basically the plastic resin material after the molding with all these white spots in it. I believe it has a glass-filled material. And then the plating sits on top of that. So in the close-up picture, you see this bit of a wavy surface. It almost looks like an ocean surface there, and that's really what you get from when we are removing the material with the laser. We get this micro-etched surface, which again creates a very, very high peel strength. You can see how the plating really grows into all these little nooks and crannies on the surface of the material and creates a beautiful peel strength there. The copper thickness that we see in most cases is probably 5 to 8 microns, could be more in some cases, but that's a pretty common thickness for an electroless copper plating process. And then on top of that, this particular application, we see a standard INIC surface finish, electroless nickel, immersion gold, in this case electroless nickel is 3 micron here, and then a very thin layer of immersion gold of 0.1 micron on top of that. Again, that's just a surface finish. The most important part, of course, structurally is the copper underneath.
Gotcha. So again, let's move up from that molecular level, and as you can see here on your screen, this is your result. So basically, this is a very simple LDS part, and in 3 steps, we molded the part, we've activated the surface of the part for activation, and we've attached the metal through electroless plating. And this is actually good that it's completed now, because now we can lead into our really cool application section. And so basically what this is, it's a cell phone antenna. Now, LDS has been huge for the telecommunications industry when it comes to cell phone antennas. Stefan, talk about why LDS has been such a big hit for cell phone antennas.
Yeah, so cell phone antennas or any other handheld devices are really an excellent example for using an MID. Because the limitation that we have is the human hand. I mean, we're trying to develop through evolution larger hands so we can have bigger displays, but it's not working so far. So right now we're kind of limited to the size of hands that we have right now. And again, a cell phone is a perfect example for this. We want all these antennas in there, but we don't want the device to get any bigger. So using those areas in the phone and actually creating an antenna and wrap it around all the corners and really make it 3-dimensional is a very efficient way to do that. Now another way where the cell phone antennas are really a good application for MIDs is also, or for laser direct structured MIDs, is that since the circuitry is being added on the plastic afterwards, the circuitry can be fine-tuned for a longer process and time. So if you're dealing with a high-volume consumer device manufacturing, you want to make sure you can move your design freeze as late as possible for best possible performance. So giving some more time to the antenna designers to really come up with the best performance. And we all want the best reception on our cell phones, don't we?
Yeah, I sure do. And again, like for me, as someone who's in a creative position, I really, to be able to have as much time as possible to fine-tune your design or your presentation or whatever it is you're creating, being able to have as much time as possible to refine it is really big. Another big industry for LDS created MIDs is the automotive industry for many of the factors we talked about, reducing part count and reducing weight. I wanted to bring up this application right here, which you'll see is inside a steering wheel. Don, there's actually a pretty cool story behind this, and I'd like you to tell that to everyone.
Well, this is a really good example of how LDS can reduce part count and thus weight also. But this part actually had at one time, the design had a PC board that was between this back panel and the button section of the part, and they simply just took the PC board out, recast the back panel in an LDS plastic, and put the circuitry that was on the PC board directly on the back panel. So you reduce the entire complexity of the PC board, a large part taken out of the final structure.
Gotcha. Moving on to another automotive application, Don, so we'll keep you here, is this motorcycle handlebar, which I think is a really good example of the 3D capabilities of MID. But talk a little bit about this part and how it works.
Once again, we have the advantages of 3D design in a human-machine interface. So in this particular case, you're wrapping a number of buttons around a handlebar, and you're basically looking to control all these buttons with one thumb. And so you're using a lot of space. You're putting buttons in a place that are accessible in a difficult situation, basically just using one thumb, and using 3-dimensional SMT and putting solder placement and the parts in place. You get a very nice, simple, single part solution to the problem.
Exactly, and as you mentioned, all those different components onto that one single part really speaks to the tune of increased functionality. And as Stefan mentioned, we're not evolving with bigger hands, we're not also evolving with extra thumbs. So being able to get all those functions onto that one single 3D part, put the wiring straight onto it, it's a pretty big deal. Another great area of application for MIDs, and specifically LDS created MIDs, is medical. Again, reducing the weight. And what I like about this example, which you see, which is wiring and circuitry for a hearing aid, is the ergonomic shape. So basically, when you're dealing with a hearing aid, you don't have a lot of space to use. And so being able to eliminate like all the different, normally maybe say you have a flex circuit here, being able to eliminate that and put that all, you can see with the matchstick comparison just how small that part is. Being able to carry, this part actually carries 3 microphones on it, all in that ergonomic shape, which is really cool, I think, of the 3D possibilities of MIDs.
And I think one of the other things that shows up in this part that's a good point is that this part has molded through-hole vias in it, and those vias are then activated with the laser and plated through, so you get front-to-back connection.
Moving on to our next application, you'll see we have security devices are big when it comes to LDS, specifically drill shields. Stefan, talk about why these drill shields are perfect for LDS.
Yeah, so here this picture shows at least a general pattern of what a drill shield does. Drill shields are usually parts that are used in devices for financial transactions, ATMs and point-of-sales devices and things like this. So of course those drill shields are there to keep any kind of intruders out of the ATM, because none of us wants to lose our PIN numbers and start to get our bank accounts cleaned out. So these devices basically are a cover that has a detection circuit on it. Now you see it's a fairly intricate circuit on it, and most applications in real life actually look a whole lot more intricate than this even. So in order to produce something like this, there's really no other technology that can do this other than laser direct structuring, because we deal with really small, long lines, and you can imagine it's impossible to flow a liquid plastic in a two-shot molding process in such a long channel without the material to be solidified before it reaches the end of the line. So again, yields would be impossible to do with two-shot molding. So again, it's an interesting application where LDS makes the use of MIDs even possible here right now.
Yeah, I agree. It really does make it possible. And as Stefan said, this is actually, we wanted to pick this application that actually had larger circuit traces than normal for the drill shields, just so you could see the complexity and the intricacy of the shapes. And then speaking of, being able to create these really thin circuit traces that you wouldn't be able to find in any other MID manufacturing processes, what's great about etching the wiring straight onto your part with a laser is LDS, pretty much any material can get down to a 6 mil trace with 6 mil spacing. That's really small. And then depending on your material, you can even get smaller than that. So that's really huge. Another application that I think is a great area of application for LDS is RFIDs and these sort of rugged RFID transponders. Don, talk about these industrial RFIDs and why LDS is great for them.
Well, using LDS and using MIDs with an RFID transponders allowed them to be moved into harsher environments and more industrial environments. The plastic, the part is applied directly to the casing, so you have a very small portable part that's also sealed and protected from the environment. It allows the inductor and the antenna to be put on the package itself and sealed in.
Yeah, exactly. And actually, a lot of times you would just have like a flex circuit behind the housing, but why not put it all together? And that also actually really helps. The range for the antenna is really increased by putting that straight onto the part. Stefan, did you have something to say there?
No.
All right. Our final application we're going to be looking at today is this really cool barometric pressure sensor. Stefan, talk about why this is a really amazing LDS application for MIDs.
Yeah, this one is really one of my favorite applications because it really shows an entirely new way of putting things together. I mean, most of you guys know we have a semiconductor in a plastic packaging, but the plastic packaging is nothing else than packaging. But here in this case, the packaging really becomes a smarter part. It does more than just being an enclosure for something. So here the semiconductor and the sensors, they're in this plastic housing there, and then the only connection in between those is direct wire bonding. And the wire bonding lands directly on the plated surfaces on the plastic part. So the entire part, consists really only of semiconductor, sensor, and the plastic housing, and of course the wire bonding. But you don't see a lead frame in this part, which is fairly interesting. So this part will then become basically an SMT component when it's done being produced. But of course, in the beginning it's only two-dimensional, but you can see here the sky is the limit, so you can start mounting sensors in all kinds of directions in a plastic part. They can be mounted in different orientations, or multiple sensors in different orientations. And again, we don't have to worry about a two-dimensional lead frame being able to catch up to this because we work truly three-dimensional with Sidon now.
Yeah, this is a great example of bringing those two sides together, mechanical and electrical, and also just look how small that thing is sitting in there on that. I believe that's a Euro right there. I mean, it's really cool how small we can, how much we can get into these tiny parts. So, I mean, that's what we have for our presentation. So I wanted to wrap things up. Basically, like the big advantages with MIDs, you're reducing your components and reducing your parts. And that really allows you to build lighter electrical and mechanical parts in actually one single part. And then again, the 3D workspace really allows a ton of design versatility that you don't have when you're dealing with flex or just traditional rigid circuit boards. Being able to open that up and really really creates no threshold for your design possibilities. Now, so we kind of looked at why MIDs are great. Well, why is LDS great? As we mentioned, it's ideal for high-mix manufacturing environments. With a two-shot molding process is great for extremely large quantities, but LDS can really get you from the prototyping to the large quantity phase, which is really nice. And then again, as we saw with the drill shield and some of the other applications, getting that really complex and intricate circuitry directly onto the parts, which really wouldn't be possible with other manufacturing methods. And finally, it's really a cost-effective entry into the world of MIDs, being allowing for lower volume production, and then also by just reducing parts. It's really cool.
Yeah, so I would like to add one thing also, and we saw this in one of the automotive applications before. It's LDS is really an interesting technology to think about parts that are already there and start to add to this. Again, many of you guys probably use a plastic part that surrounds your circuit, and maybe this plastic part can be something more than just a plastic part. It can carry a certain wiring or a connection to a sensor, or again, become part of the circuit itself.
Exactly. Now that we've recapped everything, let's say you're interested in MIDs, and specifically, checking out laser direct structuring for working with your applications. So what would you do next? Well, basically, you can give us a call. We are here, and we're willing to work with you. And I wanted to bring in Don, who some of you may end up talking with. Don, what does LPKF do in the LDS process?
Well, LPKF is the patent holder for this technology, and we manufacture the laser systems that manufacture LDS parts. We also work with plastic manufacturers and plating manufacturers to round out the entire process. What we can do for you is we can put you in touch with, depending on the product and depending on where you want to go, we can put you in touch with the LDS service provider. There's people that handle all kinds of different volumes, different types of parts, focus on different things, anywhere from small volume military type parts to large volume cell phone antennas. So we can point you in the right direction that way. We can talk to you about the design process and about design guidelines, and work with you on getting the part right for the LDS process. And if you want to integrate LDS in your production facility, if you want to bring machinery in house, we can coordinate that. We can sell you lasers. We can and coordinate the other sides of that of the process, the plating and the plastic.
Yeah, so one of the things that a service provider can also bring to the party here is really a certain cultural aspect. Again, trying to put your circuitry on mechanical parts is not always a standard given culture in every company, but again, working with a service provider could be a big help there, because they're much more used to this environment. They can really help to analyze a new design, a new MID design, especially for manufacturability. Looking at this, and they may recommend some changes that can really drive the cost down to make a part much more efficient there.
Yeah, and we work with a lot of service providers, and I think that's one of the great things. It's really bringing that expertise to really unleash your designs from 2D to 3D and get everything into a single part. Well, that's it. We are just a notch over a half hour, so I want to thank everyone for their attention. We're going to have a Q&A session in just a moment, so get your questions in. Again, hey, I love giving these webinars, and I love when we have a big crowd. We actually broke a record for registration for this webinar today, so I want to thank everyone who showed up today and was here and stayed through the whole presentation. I really appreciate it. I'm going to go ahead and actually launch a little poll just to get some feedback. And while we're launching the poll, I'd like everyone to go ahead and get their questions in. So I just had a poll. Basically, what do you think of LDS? Either you, me, it's pretty interesting, but just curious. Or maybe you think you have an application, or you maybe just want some more general information on how the whole process works. I'm going to go ahead and launch the poll. And we'll leave that open for just a minute. Go ahead and get your questions in. We're going to take a second to compile all the questions, and then we'll answer them. So hang tight just for a second. All right, so we're going to go ahead and close the poll. It looks like we got some good results. I really appreciate the feedback. But now we are going to get to our questions. So let's go ahead and talk a little bit. We have a question from David who says, how's the circuitry design? Is there any electronic design software that works with 3D and mechanical CAD?
Yeah, there's actually specific software packages that are more designed for electronic design in a three-dimensional environment, and we're more than happy to share this information with you. We'll look this up and then email that to you. But in many cases, we see designs being added in a mechanical design package, basically just a step file that's created out of those. The 3D step file with the circuitry added as basically like a paint layer, and you see this here on the screen what the whole thing would look like there.
Gotcha. Thanks, Stefan. Let's see. I have a question from Gary. Is there a generic name for these plastics? Do you follow that, Stefan, or should we get some more info about this question?
There's a large amount of plastic materials out there. The generic names, again, nylon is a pretty generic name for this, so it's a PA66 material. Those are very common, and there's a lot of different PCABS materials out there. Again, it's a large variety out there. There's LCP, pretty generic one for this. Again, of course, every manufacturer has their own brand name for these, but these are the most commonly used standard type plastic materials.
Okay, I had a question about the rough surface that we were talking about. Art wanted to know if there is, basically. They were wondering about achieving smoother surfaces for maybe RF low loss. Talk about why the rough surface, why we have that, and what we can do about smoothing up that surface, and maybe a little bit about that.
Yeah, so the surface has a certain roughness to it, and again, we need this in order to get a reasonable peel strength to the material. So it's an inherited process that we really have to create here. That's not perfectly flat because again, a cosmetic plating like you see with some consumer devices looks all nice and shiny, but again, it peels off really quickly. So this is something that we really don't want to do in this application. So in order to get an even nicer surface, we probably would have to add another layer of plating to this that really smooths out the surface, and there's some plating applications that can do that for you.
Gotcha. And then a lot of people, we have questions from several people asking about the fine line trace and space capabilities, and I believe I touched on the really common measurements we can get to is 6 mil trace and 6 mil space, but either of you guys want to comment on just how fine we can get with LDS?
Yeah, the 6 mil trace and space is a pretty common used process right now, and that's limited not by the laser systems producing those lines. Those lasers have very high resolution. We can make much smaller lines. But however, since we use an electroless plating process, which is an additive process, so we grow copper in those areas. We need to make sure we adhere to the limitations of that particular process. So the general rule is the finer you want to go with your lines, the less plating we would recommend, otherwise yield would start to suffer a little bit. So having a really thick plating and a really fine resolution is usually a bit of a conflict there.
Gotcha.
It's a combination of the types of plastic you use and the plating process. You can get thinner. What is kind of the...
Yeah, you can probably push the envelope a little bit lower, but again, in this case, you could probably start to compromise the plating thickness a little bit. But again, in an area of the 6 mil space and trace is probably pretty common right now for these applications.
Gotcha. And then I had a question coming in from Gary if we could address the throughput of a typical LDS laser system.
That's a great question, Gary. The throughput really is that varies with the size of the part and most importantly with how much area is structured on that part or how much circuitry is on that part. So if we imagine a part that's the size of a hubcap and everything is covered on that, then of course the throughput of the laser system would take a bit more time to do this. Most common applications that we see in consumer electronic applications typically have throughputs of a few seconds. More complex parts, maybe we see something up to 20 or 30 seconds if it's really complex circuitry, bigger drill shields and things like this. But again, it really depends on how complex and how big the circuitry area is on the part itself.
Okay, gotcha. And I have a big announcement to make. 1,000 points goes to @sectionisclosed. We have a question coming in via Twitter. And he wanted to know if we increase the current, with what rate will the thickness of the copper deposition, how will that affect that?
Yeah, so definitely, for if you want to run a lot of current on an LDS part, you would have to probably create wider traces for this. And we have some graphs and schematics and calculations for this where we can help you with that. So if you want to run a lot of current on a part that has fairly thin plating, really the only way to do this is to make the lines a little wider. However, the good thing is we use a lot of real estate here on plastic parts that usually hasn't done anything in the past. So in many cases, there is the real estate available to make those lines a little wider. This is typically common if we see LED lighting applications or other lighting applications, because those need a little bit more current than we see with common RF antenna applications.
All right, pretty simple question coming in here from David. He wanted to know if it's possible to do multi-layer circuits, 2 to 4.
Not to my knowledge so far. So again, the MIDs and the laser structured MIDs, they basically add a circuitry to a plastic part. So we use all the sides of the plastic part, and as we see in some of the applications, we can also create through holes to have an electric current, basically travel through the part and on the other side and continue on there. But it's really not a process that's designed for multi-layer or replacing a multi-layer circuit board in this case.
Gotcha. I have one more question from David, who wanted to know, he wanted to maybe talk a little bit more about the service we provide, basically from prototyping to tools, and what exactly do we quite do?
Well, we are laser manufacturers, and we talk about the technology itself. We have engineers that can help you with both the design of your part, and we can look at the design and tweak things and talk about recommendations. To some extent, we can put you in touch with service providers who are very experienced in helping you design parts. Some of them do complete design build. Some of them take your design, maybe help you work with it a little bit for manufacturability, and build from there.
Maybe anything specific into prototyping, because David brought that up.
Yeah, so for prototyping, again, we can help you with some prototyping here directly, or we can, again, get you in touch with the service provider that does these types of things also. But again, we also help you if you decide to really bring in LDS technology in-house and really start producing the stuff. We will make sure we'll help you with this entire process too, anything from the design process and training of your design team all the way to laser systems, and we'll help you with appropriate plating lines, or help you with consulting on your existing plating lines if you have some already.
One of the things we didn't talk about is LDS. LPKF has a real push right now in LDS to enable prototyping. We have some products coming online that are very oriented towards prototyping, and certainly 3D printing has become a big part of that. Both printing in an LDS plastic directly, or using a coating on a printed part for a quick prototype without developing an entire mold.
Yeah, thanks, Don, for making that point. The 3D printing really is a big game changer now for LDS parts, because we can now create LDS parts directly in a 3D printer, which is a fantastic tool to have. So you can use an existing part and step file, run it through a 3D printer, and you have a part that can be immediately laser structured and plated. So that's a real little change in that. So.
Yeah, and I'd like to say my thanks to Don again too, and I'm sure Joseph out there is extending his thanks to Don, because Joseph actually had that question. Jan Willem wanted to ask, what kind of laser power and wavelengths are applicable to LDS?
That really varies on the different plastic materials there. Most of the laser systems that we have are operating in the near infrared area there. Again, laser power very much varies with the different type of plastic materials. There's really no standardized answer to that type of question. So different plastic materials will require different laser power, different laser recipes or tools, as we call them.
Again, hey, I wanted to thank everyone for submitting their questions. We have a ton of questions, so if you haven't heard your question yet, we'll probably get to it. So, and if not, if we can't get to it by 12, we will follow you up with email. So, Leonardo wanted to know, with 3D designs, how is ICT in circuit test and AOI for SMT devices addressed? Could you also please talk about impedance-controlled traces?
This is probably a question that I would have to defer to a service manufacturer that does that. There's a ton of people out there that do these things, that produce MIDs and LDS and other technologies, and those very well have the process for the manufacturing process, both for the assembly as well as for the impedance control and dialed in. So again, this is probably something where we have to refer you to a service provider there.
All right, let me scroll through these questions here. David wanted to know, could we send a service provider details? And that's something we can, as we mentioned, we'll get in contact with you if that's what you're interested in, David, and we can help you with that. Okay, David had a question. With finer traces and spaces, he says maybe 50 micron, can you burn the channels deeper to allow thicker copper deposits?
Well, it's not necessarily always a process of burning the channel deeper. We're not filling the channel per se with copper. I mean, the copper does, the channel is there, and the copper is below the surface of the material to some extent, but it will grow above the surface of the material also. That's a result of how long you're basically leaving in the tank and the reactivity of the tank. Typically, 5 to 8 mils is or 5 to 8 microns is pretty standard in electroless plating.
Okay, you wanted to get this question from Mark here?
Yeah, sure.
So Mark said he'd like some more information about LDS-compatible 3D printing. So,
yeah, so the 3D printing is a process the Stratasys is promoting right now. So they're actually printing with their 3D printers material directly in a PC-ABS grade material. That's an LDS grade type. So again, the part can be made directly in this 3D printing process, which is again a great help to get an existing part or get a part and put some circuitry on this right away. So.
Gotcha. And then I have a couple questions about materials. People just basically want to know if there's materials for medical applications and also for automotive. Specific materials.
Yeah, there's specific materials that are that these industries prefer more than others. Again, we see in the consumer electronics world. Again, we see a lot of people who like PC-ABS because it's an inexpensive and fairly strong material. In the medical world, we often see the demand for higher temperature type materials or materials that allow micromolding. LCP again is a good example for this. If you want really small parts of very intricate mechanical features, and LCP is probably a better material than others. In many automotive applications, we see, for example, nylon grades like the BASF Ultramid material, because it's the price is reasonable and the temperature stability is a little higher than some other materials there too. So again, it really depends on what the type of application is. There's other new materials coming online too. There's PEEK materials coming online, which is more designed toward medical applications. There's COP materials coming online for high frequency antenna applications with high performance. So again, it goes really in all kinds of different directions and depends on the application.
Yeah, I know that we're always working with material providers on these updates. I know that we update our material list on our website, like I think every month or two.
Yeah, exactly.
Gotcha. Let me give a second for the last couple questions, and we'll get to those. So hang on just a second. One question we just got in from John, actually looks like just a couple minutes ago he sent it in. He wanted to know if the circuits can be sealed after plating to protect exposure to moisture.
Actually, I've seen some applications that do this, where once the circuitry is formed completely, that there's just basically a coating layer going on top of the entire part that can be for aesthetic purposes or, like I said, for protection from moisture or any kind of environmental influence. So, yeah, coating on the plastic part can be done absolutely after the circuitry has been applied. So.
Gotcha. Looks like we're running to the end of our questions list. I'll go ahead and give a minute or two. So if you have any final questions, get them in. We're going to respond to all the questions via email as well. So if we missed your question, we will address it in follow-up. But if anyone has any questions they want to get in right now, we'll hang on for a minute and get them in. All right, thank you to the 30 of you who have stayed through this whole questions period. It looks like questions have slowed up. We haven't received any in the last couple of minutes. So again, thank you, everyone, for stopping in today. We're going to follow up with all questions again via email. And you guys have anything to say as we close? Just thank everyone for stopping by today.
Yeah, thanks again for staying the whole time, and I hope it was informative there. And if there's any more questions, again, please feel free to email us anytime also after the webinar. Thanks.
Yeah, just feel free to contact us, and we'll get your questions and get you connected with the right people, and thanks for coming by.
All right, thanks, everyone.